Okay, we're looking at this CAPM practice problem. So we're looking at drawing accurate graphs for these two motions, position and velocity graphs. So it's generally easier, I think, to start with the velocity graph, and we can certainly use the numbers on the velocity graph to get the numbers on the position graph. So we're starting, our car's starting from rest, which means this is where my initial velocity is going to be. And I'm going to speed up to 30 meters per second in 15 seconds. Okay, so if we have a constant acceleration, it'll look like this. It's 30 meters per second, and this is 15 seconds. By the way, this is a nice way to draw the graphs to save yourself a little time. Make the sort of proportions right, and then just sort of mark the values you have. Don't get too precious in the scaling. We're just trying to get the idea across. And then it maintains that speed for 30 seconds. So this should be a longer segment. And that'll end us at 45 seconds there. And then it's going to come to a stop in 5 seconds. So that'll end at 50 seconds. Alright, now that's everything there is for the velocity graph, but the position graph will be a little trickier, both in shape and in numbers. So this is our position, which we'll measure in meters. I'm going to start at 0, but you can start anywhere you want. We're going to make it line up along the time scale. Okay, so I know that in this first shape I should start with a flat graph because my initial velocity is 0, so my initial slope here should be 0, and then that slope should increase because this velocity increased. Okay. Now I don't know how far it went in that unless I go to the velocity graph, and the displacement is the area between the velocity graph and the axis. So that first delta x would be this area, which is 1/2 times the height of that triangle, which is 30 meters per second, times the length of that triangle, which is 15 seconds. So that'll be 225 meters. So this should be at 225. Now in the next segment, I'm at CVPM, which means this is going to be linear, and it should be linear with the same slope that that one ended. So maybe make it a little bit flatter. Okay. Now I can have a nice constant slope. Okay, I'm going to run a little bit into the text. That's okay. But I don't know how far this spot is. Okay, what is that? What is that place? Well, I need to look again for displacement. I'm going to look at the area. Okay, this whole area here. Okay, so this displacement is going to be this area, which is 30 meters per second tall times 30 seconds long. So the delta x in this segment is 900 meters, which means that I've changed 900 meters from the beginning, or from the beginning of that interval, which is here, which means this is 1125 meters. So this is about the change in position. That's what the delta x really is, not the position. So I don't end this part at 900 meters. I end it at 900 meters past where I was when I started this part. And then the last part here, I need to end at a velocity of 0, which means I need to end flat, but I start moving and then I slow down. Okay, so it looks something like that. So it's a parabola, a line, and another parabola. But how far did I go? Again, delta x is 1/2. That triangle is still 30 meters per second tall. This time it's only 5 seconds long, which will give me 75 additional meters of motion. So this displacement is 75 meters, which means I ended at 1200 meters. All right, that's that graph. If I look at the rock, it seems like I'm given less information here, but there's actually definitely enough info to solve the problem. So it's dropped from rest. We're going to take positive as up, which means that my velocity is going to end up being negative, so I'm going to start rest here. Okay, and if I'm moving downward, my velocity would be negative. So it's going to speed up, right, as things do when they fall. And then I'm going to end up at some final velocity. The final speed is 30 meters per second, so the velocity is negative 30 meters per second. And this is 3 seconds later. on the time axis. And the acceleration here is the change in velocity, which is there, negative 30 meters per second over that change in t, which was 3 seconds. So the slope of that velocity graph is the acceleration, and it's negative 10 meters per second squared, just as it should be in free fall. I mean, if this is a real rock, it'll be 9.8 meters per second squared, but this is close enough. 10's close enough for problems. Okay, so we have the velocity graph. Time for the position graph. Okay, we'll again make the time scales line up. So this one should start flat and then get more and more negatively sloped. Okay, so I'm going to start it up a little higher with a flat tangent line, and then it should get more and more negatively sloped, right, like that. Okay, the steeper the slope gets, the faster it's going. That's what we see from there. You can call this 0 if you want, or you can call that 0. It doesn't really matter. That's pretty arbitrary. But what's important really is what this displacement is, and the displacement we get from the area between the graph and the axis. And that triangle is negative 30 meters per second tall and 3 seconds long, which will give me negative 45 meters. So I either end at 45 meters, or you could say this is 0 and you began at 45 meters, or anything else. As long as this delta x is negative 45 meters, it will be fine and consistent with the given info. All right, that's that.